I'm going to describe a pressure temperature diagram for a binary mixture. But first, let's look at some diagrams that might be more familiar, because essentially what we have is a three-dimensional structure to represent vapor-liquid equilibrium, in which phases what the compositions of vapor and liquid phases that are in equilibrium. One axis is pressure and one is temperature, and the third is composition. Many of you are probably more familiar with looking at a pressure mole fraction diagram or a temperature mole fraction diagram. And so these are slices. So the diagram on the left, pressure versus mole fraction, where now the liquid is blue and the vapor is green, is a slice at just one temperature. And there's a whole set of these that exist at various temperatures. Likewise, the diagram on the right is temperature versus mole fraction. And again, we're looking at just one pressure. Of a different pressure, a different slice, if you like, of that three-dimensional structure, which three-dimensional structure that looks like a mitten, basically, at an angle in this three-dimensional phase space. So the third slice would be fixing the mole fraction and looking at pressure versus temperature. And this has some more information in it. The two diagrams we're looking at here, we only use where we have saturation pressure existing. In other words, we have to be below the critical pressure for each of the components. And likewise, the diagram right, we have to be below the critical temperature to have a saturation pressure. So let's look at now the other slice, the constant mole fraction and pressure versus temperature. So in this diagram, instead of just showing one slice, like in the previous diagrams, for example, a slice at constant temperature, here I'm showing a number of slices at different mole fractions, but pressure is on the y-axis, temperature is on the x-axis. The pure component, and this is a different mixture than the pressure mole fraction and temperature mole fraction diagrams I showed you. This is for ethane, heptane. Pure component here for ethane, pure component heptane. A couple things to notice. We have values above the two critical pressures. We still have phase equilibrium for a range, and we have a critical point for a mixture, which in this case can be dramatically higher than the highest critical point for either of the components. And then if we look at a given point, such as here, then the mole fraction of liquid, which is blue, of 0.5, is in equilibrium with the mole fraction of vapor of 0.9 at a pressure of about 5.5 megapascals and a temperature around 390 Kelvin. The other thing to notice about this diagram, for some compositions, if I draw a vertical line, let me stop and do that. So note I've drawn a vertical line that says mole fraction, vapor of 0.8 at the temperature of about 430 Kelvin. Has two pressures where we have phase equilibrium, and the mole fraction liquid phase is going to be different, these two conditions. So the same temperature actually has more than one solution when we fix the vapor phase mole fraction, namely at different pressures we have phase equilibrium with different liquid mole fractions. And you can see there's a range. We can do this at on the 0.8 line to 0.7 to 0.9. We can draw a vertical line to identify which temperatures we can actually have more than one solution. But keep in mind, what we're showing here are slices on this pressure temperature diagram.